Hey guys, Miss Marusik here, and in this video we're going to talk about calculations involving our integrated rate law formulas. Now in these first two examples here, we're going to see problems where they actually give us some information about our order so that way we can go and calculate using our formulas. We'll see in our later two examples that they're going to give us some graphs to analyze so that we can determine what our orders might be and therefore what formulas I would use. So let's look at this first one here. They give us a reaction that's occurring, and they give us a rate constant K of 0.0480 seconds to the negative first, molarity to the negative first. And the first question asks, what would be the order of the reaction? Now, it gives us kind of a hint here to use the units of K. If you remember, K always has the units of time to the negative first, and then molarity raised to the negative overall order minus 1. Well, if our overall order minus 1 is equal to 1 here, then that means here my overall order must be 2. And since there's only one reactant, that means that NOCl must be second order. So once I see that that reactant is in second order, that means I know what integrated formulas I could use. Obviously, I would know that rate equals K, the concentration of NOCl in brackets raised to 2, but that formula, those differentiated formulas, only work if I am given rate and concentration data. If I look at my example here on part B, I notice that instead of rate and concentration, I'm given concentration and time. And so I can't use that rate equals K, concentration of my reactant raised to the order. I can't use that formula. Here I'm going to need those integrated formulas whenever I see time is involved. And so that's where I would then go and consult my formula chart. And I would want to remember that this first equation is for zero order. The second one is for first order, and this third equation here is for second order. And so that means I want to use this third equation here, that 1 over the concentration of A at some time minus 1 over the concentration of A at a time of 0, the initial, equals our rate law constant K times T. Now, one quick thing about T. The time units must match whatever time units were used in K. So if you notice back up here, the time was in terms of seconds in K. And so when I plug into this, I want to make sure that that time is in seconds. If you notice, they give us 15 minutes. And so one of the first things I did is I converted that 15 minutes into seconds. So then once I did that, it's just a matter of plugging in and solving for my variable. So it gives me here that my initial concentration of NOCl was 0.400 molar. And so I want to plug that in for the initial A right here. I then have the value for K from my problem up above. So I'm going to plug that in. I'm going to plug in my 900 seconds. And so then what we're going to try and do is solve the concentration of A at our time T of 900 seconds. Now, to solve this algebra here, I'm going to go ahead and show you how I would do it in my calculator. The first thing that I would do is multiply these two guys on the right-hand side. So my 0.0480 times 900. Okay. Then I'm going to bring over this minus 1 over 0.4. Now, to bring that over, since it's subtracted, I would end up adding it to my value. So adding 1 divided by 0.4. And you notice that I kind of put this whole thing into a parentheses in order to address my order of operations here. So that gets 45.7. But that 45.7 is going to equal 1 over A sub T. And so in order to solve this, I'm going to need to do 1 over 45.7 in order to get my A sub T. I did go ahead and run this for 3 sig figs because it kind of looked like a lot of the things that they gave me were in terms of 3 significant figures. So then the second part of this question says, hey, in an experiment at 200 degrees Celsius, so it's the same temperature, so it'll be the same K, the initial concentration of NOCl was 0.400 molarity. How many seconds will it take for the concentration to drop to 0.150? So what that means is that plugging into this equation, I want to find out what the time would be when my concentration of A gets down to 0.150 molar. My initial concentration was that 0.400 molarity, same as it was in the previous problem. And then my K is still the same, 0.0480. So to solve my math here, this time I'm going to solve everything on this other side. Notice I always kind of solve the side opposite of my unknown variable first. So I'm going to have 1 over 0.150 in parentheses minus 1 over 0.4. I'm going to get an answer there. And then in order to get t by itself, I would want to divide over this 0.0480. And so that gets me a time of 86.8 seconds. So again, I rounded to 3 sig figs. Now this last one here says, hey, if my initial concentration again was 0.4 molarity, calculate the initial half-life. Now in order to do this, this one is second order. So remember, I cannot use this half-life equation that's on the chart because that half-life equation is only true for first order. It's not true for second order. Also notice the fact that they asked us about initial half-life because remember, for a second order reaction, that half-life changes as the reaction progresses. So this is only what that first initial half-life would be. So what I did was I plugged in my 0.4 initially, but then I said, well, hey, half-life is the time it takes for that to get cut in half. What would 0.4 be cut in half? Well, cut in half, that would be 0.2. So I want to figure out the time it takes for me to get down to 0.2 molarity. And so I would solve this algebra the same exact way I solved the previous problem, and I can see that that gets me a time of 52.1 seconds. All right, let's look at the next one. On this one, they pretty much flat out told us our order. They said, hey, we have this reaction here and it follows first order kinetics. So awesome. I know I'm going to be using first order here. It goes ahead and gives me my rate constant value at a particular temperature. So then I'm going to go and figure out my formulas I would want to use. Obviously, I know rate equals K, our H2O to our reactant raised to an order of 1. But the problem is again, that rate law formula that we're used to seeing only works if I have rates and concentrations. Here I have concentrations and time. So anytime I see that I have time, I need to go figure out one of those integrated formulas to use. And so what I would do is come over here to my formula chart and I would say, hey, this first equation, that's for zero order. This one is for first order, this one is for second. So if I want first order, then I want this middle equation right here with the natural logs. So I'm going to be using that the natural log of A at some time minus the natural log of the concentration of A initially equals negative KT. So then I go and start plugging everything in. The initial molarity was 0.2, so I plug that in for my A sub 0 here. Also, they gave me the K value up here in the original problem, and so then I just plug that in here. Also, I noticed that this says 10 minutes for my time. Well, if you look back at your K, it had minutes as the unit, and so therefore I could just leave that as 10. I didn't need to convert it into seconds because my time units already matched. Now this one, the algebra gets a little interesting. Let me explain why. First off, let's talk about getting this ln of A sub t all by its lonesome. So I'm going to start by solving the things on this side over here. So I would do a negative 0.0410 times 10, which of course gets a negative 0.41. And then what I'm going to do is I'm going to bring over this minus natural log of 0.2. So I'm going to go ahead and convert that into a number here, or you could just add natural log of 0.2 over. I'm going to go ahead and do it that way. So I'm going to take this and I'm going to add over. For those of you that have never used the natural log button, you can see it's just got ln right here. So I just hit that and then plug in my 0.2 in the open parentheses that they gives me. So there's where that negative 2.019 is coming from that I see right here. But that is equal to this natural log of A sub t, which I just went ahead and put ln of x for those of you that are more familiar with seeing x as far as algebra is concerned. Now, in order to undo a natural log, to solve that variable where my x is with that natural log, I need to set both of these as an exponent on e. E is the way to undo our natural log. And so when I do that, what happens is that e and the natural log of x ends up just equaling x. And so then what I want to do is I want to solve this e to the negative 2.109. Now, since I have that number in my calculator, what I'm going to do is I'm going to plug in e. And for those of you not familiar with e, it is right here above the natural log button. So I want to hit second and that natural log button, and that'll put e into my calculator. And at this point, I can put the negative 2.109, or what I can do is do second and then the negative button, because that'll put the answer in there. And then I just hit enter, and I see that that gets me my final answer for the concentration of A at that time of 10 minutes. By the way, I know some of y'all that are in Algebra 2 might not be as familiar with this depending on what point in your curriculum you're at. And so keep in mind that this is how you would do it. This is the only one where the algebra gets a little weird, and so I thought I would kind of walk you through how to do that. All right, on part B here, they're asking us how long would it take for half of the H2O2 to decompose. So they're asking us here about that half-life time. So again, you could go back to this original equation here, plugging in 0.2 molarity for your initial concentration. And then what you could do is say, well, half of that would be 0.1 molarity, and end up solving for T after you've plugged in your K. And that would totally work. However, you do have another option here because this was first order. Don't forget that on your formula chart, we have a half-life equation if we have a first order reaction. We can get that time by putting 0.693 over our K value. And so because this is first order, you could also solve this one using this equation right here, plugging in your K value of 0.0410. So regardless of which method you used, you should be getting the same exact answer of 16.9. By the way, that 16.9 will be in minutes because, as a reminder, our K unit also had minutes in it. All right, let's go ahead and look at the next page where we'll start to look at some of these problems that involve graphs. So what they've done here is they've given us a reaction, they've given us some time and concentration data, and then they've plotted that time and concentration data along with also plotting natural log of concentration and time and 1 over concentration and time. And so what we want to do is, based on this information, we want to figure out our correct orders and then end up calculating with this data. Now, again, as a reminder, because this is time data and not rate data, that's our key indicator that we're using integration formulas here and not just our regular differential equation. So we got to be careful to make sure we use those integrated formulas that are on our formula chart. So the first thing I want to do is ask myself, well, what order do I have here? And so that's where I want to look at these graphs and ask myself which graph is presenting a straight trend line for the data. And if I look here, I notice that the natural log of concentration graph is the straight line. And if I go think about my formulas here, remember this first equation with just concentrations in my straight line, that would be for 0 order. Natural log of concentrations in my straight line equation would be for first order, and then 1 over concentrations for my straight line information would be for second order. So because the natural log graph is the straight line, I can make a really good assumption here that this reaction is first order. Now, if you didn't have these graphs, but you had this data here, could you go and graph the data? Sure, that's probably what you would have to do in a lab situation. You could also run a linear regression on these combinations here, for those of you that are familiar with doing that. But on the AP test itself, you would be given these graphs already done so that way you could select which one was the correct order. So here's the kind of statement you would want to make to justify your answer. You would want to say that the reaction is first order with respect to N2O5. So we stated what the order was. As the graph of natural log of N2O5 versus time has the most linear trend. You would want to state which graph told you this information and why that graph told you that information. So I specifically stated which axes I used to determine what was the most linear trend in order to determine that it was first order. You want to make sure you make all of those statements when you're justifying your answer there. And so what that means is that for this reaction, rate equals K in brackets N2O5 raised to an order of 1. Hooray! However, here's the problem. I can't use this for any of that time and concentration data to go solve these other things because, oh wait, I don't have rate data. All I have is time data. Now, if I knew K, could I plug in my concentrations and go solve my rates? Sure, I could, but I don't have that yet. And so I'm going to need to get a little creative with the data that I have. So this is where I would want to select the correct integrated formula to use, just like we did on those previous problems. So as a reminder, because we said the natural log graph was the straight line, this is the integrated formula that I would want to use to solve all the rest of these problems. So now the next question says, hey, determine the value of the rate law constant, which is K, with units. And it wants us to show our work. Now at this point, we are given data in a table here. So you could definitely use this. If you didn't have this data here, but you had your concentration and time graph, as long as this was really easy to read, where the points maybe fell at really specific intervals where it was easy to kind of pick out reading your points, you could obviously read your graph. But since I have this table of data here, I'm going to use that instead. So I have exact numbers versus just approximating from this graph over here. Okay, so I'm going to pick any time and concentration to use. So I'm going to need the initial one to plug in here for A sub 0, but when I pick what to plug in for T and the concentration at T, I can pick any data points off this table. Now, I'll be honest, I usually pick the next one right after a time of 0. Okay, but you could pick a time of 2400 seconds. You could pick a time of 3600 seconds. It doesn't matter. You just want to pick a second set of points. Now, depending on what set of points you use, you might get a slightly different value for K, but it should pretty much round to exactly the same constant. So what I did is I said, hey, I'm going to use the time of 600 seconds. And at that time, I had a concentration of 0.0274. So then again, all I'm going to do is solve for K. So to get K by itself, what I'm going to first start off by doing is plugging in this information that's over here on the opposite side of it. So I'm going to have natural log of 0.0274 minus the natural log of 0.0365. Make sure to close those parentheses after you do those. Otherwise, it'll give you some errors and it'll look all crazy. So I'm going to get an answer for that. And then what I want to do is I want to get the K all by itself. And so I want to divide by a negative 600. So don't forget to get rid of your negative as well there. And when I do that, that gets this value here, which I've rounded to 3 sig figs at 4.78 times 10 to the negative fourth. As far as my unit is concerned, remember I would want to use the unit of time, which is seconds, raised to the negative first. And then I would normally have molarity raised to the negative overall order minus 1. But think about your overall order here. Your overall order is 1. So 1 minus 1 just ends up being 0. And so I didn't put molarity to the 0. I just left that part of the unit off. All right, the next question says, hey, what is the concentration of N2O5 at 15 minutes after the reaction began? So it's giving me that time here, 15 minutes, but I notice that's in minutes and K is in seconds. And so what I first did is I converted the 15 minutes into seconds. So then I plugged in my K that we just solved. I plugged in my time of 900 seconds. I plugged in my initial concentration of 0.0365. And what I'm going to do is I'm going to solve for that A sub T. And so to do that, again, what I would do is I would start off by this information here on the other side, negative 4.78 second E negative 4 times 900. Then I'm going to add over this natural log of 0.0365. And this number then would equal ln of x. Now this is where, remember, if you raise both of these as the exponent to a coefficient of e, what would happen is e to the ln ends up just giving you that x. Okay, and so then I would have e raised to that exponent. And so what I'm going to do is I'm going to take this and I'm going to do this second ln, which puts the e in there, and then I'm going to raise it to an exponent. That's my answer from the previous question. And so that gives me my molarity at that time of 900 seconds. Now on these, you should be able to kind of ask yourself whether or not your answer makes sense. And here's why I say that. You've got some data up here. Think about it. 900 seconds would fall between 600 and 1200 seconds. So my concentration value should be somewhere between 0.0274 and 0.0206. And in fact, my concentration is between those two values. All right, the next question asks, hey, at what time is the concentration of N2O5 equal to 0.00750 molarity? And so I plug that in for my concentration of A at some time. I'm going to try and figure out what that time is in correspondence to it. I plugged in my initial concentration here according to my graph. And then I also plugged in my K value. And so then what I would want to do is solve for T. So again, to do that, what I would do is I'm going to solve all this on the other side. So I would have ln of 0.00750 minus the natural log, of 0.0365. And then I'm going to divide over my K. So divided by a negative 4.78 second e to the negative fourth. And I see that gets me a time of 3,310. And again, my unit of time should match up unit-wise with K. K was in seconds, so this is going to be in seconds. Now again, I can ask myself if this makes sense. I see that that 0.00750 falls somewhere between this 0.00860 and 0.00640. So my time should be somewhere between 3,000 and 3,600 seconds, which in fact, lo and behold, it is. All right, the last one here on this problem says determine the initial half-life of this reaction. So because this is first order, you do have some options. What you could do is say, hey, if my initial concentration is 0.0365 molarity, as it's been for all of these, what is the time when that concentration gets cut in half? And you could solve that for T and totally get a correct answer. However, since it's first order, you do also have the option of using the half-life equation that's on your formula chart. And so if you do that, you would have 0.693 over your K value. And remember, our K value we calculated back up here. And so once I substitute that in, I could then solve for T. That gets a time of 1,450 seconds. Again, seconds is our unit because it matches up with K. All right, here's what I want y'all to do. There is a problem involving concentration data with time on the next page, along with some graphical analysis. So what I want you to do is to take a moment and pause the video and see if you can try out this example. All right, so pause that video, Go try it out yourself. See what you can do. All right, did you pause it? Did you go try it out? I sure hope you did, because I promise you're going to feel a lot better about these if you actually tried it out yourself. So with that said, the first question said, hey, determine the order of the reactant and justify your answer. Well, looking at my graphs, I noticed that the 1/, concentration versus time graph is the straight line, and so therefore it would make sense that this is second order. So I said the reaction is second order with respect to NO2, as the graph of 1/, NO2 versus time has the most linear trend. So then my rate law expression is rate equals K, my concentration of NO2 raised to an order of 2. Now, the problem is I don't have rate data, and so therefore I need to use some integrated formulas in order to figure out what these rest of the components would be. So I know that because it's second order, this is my appropriate integrated equation. And so you'll notice that I use that equation on all the rest of these problems. So the next one says, hey, determine the value of the rate law constant with units. So what I did is I used my initial concentration here, and then I used the one right below it that occurred at a time of 60 seconds. And so then I just rearranged to solve for K. So what I did is 1/0.00683 minus 1/0.0100, got that answer, and then divided by 60. And when I get that, again, I rounded for about 3 sig figs here, that got 0.774. My unit is the unit of time raised to the negative first, so this was in terms of seconds according to my graphs. And then molarity raised to the overall order -1. Well, here, overall order was 2. 2 minus 1 would be 1. So that's why it's raised to the negative first. So then the next one says, hey, what is the concentration of NO2 after 8 minutes? So I did need to convert that 8 minutes into seconds. And so I multiplied it by 60. And so what I wanted to do then is figure out for 480 seconds, what would the concentration of A be at those conditions? So again, what I would do math-wise is 0.774 times 480, get an answer. Then I'm going to add over the 1 divided by 0.01. And then that's going to be equal to 1/, my concentration of A. And so therefore what I want to do is I want to do 1/, this answer to get my correct answer here. So that gets me a concentration of 0.00212 molarity. By the way, that kind of makes sense because it is a time that's further along than this 360 seconds. So it should have a concentration that's smaller than 0.00264, which in fact it does. So then it asks, hey, at what time is the concentration equal to 0.0045 molarity? And so what I did is I plugged that in for my concentration of A at the time that I'm trying to solve for. And so here I would do 1 divided by, oops, let me scooch this up here, 0.0045 minus 1 divided by 0.01. And then to get T all by itself, I would divide by my 0.774. And that gets right around 158, and again, seconds, because that matches up with K. Finally, to determine the initial half-life, again, here I cannot use that formula that's on our formula chart because this was not a first order reaction. And so therefore, I have to do it in the method where I plug in 0.01 for my initial, and I half that to figure out what time that corresponds to. Remember, this half-life would change over the course of the reaction, and so we're just calculating what this would be at the beginning. And so I would approach plugging it in the same way I just plugged in the previous one, and that got a time of 129 seconds. By the way, one last thing I want to mention. Now that I have my K value, I could also plug in K here, plug in these concentrations, and determine what the rate would be at those concentrations. So keep in mind that now that I know K, I could go back and calculate with this if I wanted to. So you've got all kinds of options for calculating. I could also, with all this information, go and figure out, say what the correct mechanism was. I could pick a mechanism based on having to match up with having an order of 2 for NO2. There's all kinds of ways that all of these things tie together. And so what you'll see is that more likely than not, these problems will ask about a variety of things where you're going to see a combination of things from the last several videos that we've done. All right, I hope you're feeling good about calculating with the integrated rate law. If you have any questions or need any help, please feel free to email me. Bye, guys.